Hello, my name is Michael Stahl. I work for Allotropia and want to talk about something I've worked on during the last year about ODF encryption. ODF has supported password encrypted documents since the very first version. And the ODF package is based on a zip file, and some might note that there is also in the pkzip specification or app node, whatever it's called, there is some encryption there, but this ODF encryption was always completely unrelated to that. For ODF, it's specified in the part 2 of version 1.3, which is the package part. There is a chapter there about encryption. And the way it works is that every entry in the ODF package is encrypted separately. And for this encryption, there are various parameters needed. These are then stored in a special file called metainf manifest.xml. So this contains an XML element for every entry in the zip file with all of the parameters that are required to decrypt the file. So how does this work in detail? Yes, scary diagram. So at the top, the rectangular boxes, you can see how the data is being processed for a zip entry. So it starts out as plain text. Then it is compressed in the usual way. We get the compressed plain text. Then it is encrypted. And the encrypted data or ciphertext is stored in the zip entry. So that was the boxes at the top. At the bottom, you see the big rectangle, that is the manifest XML. There are various encryption-related attributes stored there. And in the middle, the octagonal boxes, those are the special additional data that is required for the encryption. So at the left side, the green boxes, that is what the user provides. So the user provides the plain text and a password. So the first thing that is done here is that from the plain text we compute a hash of the first kilobyte of it, and this is stored in the manifest. And we also store the original size. And this just so that you can, when you decrypt it, you can quickly tell if the password that the user entered was correct. What you can see on the arrow there is written SHA-256-1K, that is the algorithm that is used for the hash. An asterisk next to it, that means that this algorithm is also stored in an XML attribute, so the implementation can choose which algorithm it's using here. So parameterizable, everything that is marked with an asterisk here. Then the other thing that is provided is the password. So in the first step, the password is hashed with SHA-256. This gives the hash password, and then from this the encryption key is derived with a key derivation function, and this was using PBKDF2 with 100,000 iterations. And the way PBKDF2 works is basically it is running a hash function, and the output of it is then run through the same hash function again, and you iterate that 100,000 times. This needs an additional input, a bit of random data called salt. Then, okay, we have the encryption key now, and in order to do the encryption, we need a second bit of random data. This comes from the operating system. This is called the initialization vector, and both of these bits of random data are stored also in the manifest because they are required to decrypt the file. Okay, now with the key and the ID, we can do the encryption. This is using AES 256 in CFV mode. And we get the encrypted data. So, what problems are there with them? So the main problem that motivated the whole project was that the key derivation is done once for every zip entry. And this results in very bad performance of the encryption. And closely related is the third problem, which is that the key derivation function that we use, PBKDF2, only uses CPU time, so it's running a SHA hash that is using CPU, but it does not use memory. And this means that since about 10 years or so, you can run SHA hashes very quickly on GPUs. You can try to brute force the passwords. You can try out thousands of passwords in parallel on the GPU, and that speeds up the brute forcing a lot. And so, in order to prevent the password from being brute forced, we had to increase the number of iterations of the PBKDF2 to such an extent that if you put a lot of images into your ODF file, you can wait for tens of seconds to save it encrypted. So if you just have a plain text file, it's not too bad. But yeah, obviously this is a problem. We have this bug here since 2016 or something, when I increased the number of iterations. The second problem is that the ciphertext that is stored is not authenticated. The problem here is that an attacker could modify the encrypted document in such a way that when you decrypt it, you don't notice it has been tampered with. Then there are some additional minor problems with information that is leaked in the encrypted file. The plaintext checksum that I mentioned on the previous slide is, of course, not ideal. The other problem is that the names of the entries in the zip file are also stored in plaintext. Okay, and what quickly became apparent after looking at all these problems is that any solution for the problems is going to be incompatible. That is, you cannot open an ODF file that is stored with any new way of doing things with an existing LibreOffice version. That's just a constraint we have to live with. Okay, so then we looked a bit for what existing ideas are out there, what has been proposed before. So we noticed that in order to mitigate the information leaks, some 10 years ago, there was an functionality added for when storing the encrypted documents, some comment of random data is inserted at the start of all of the XML files, so that the checksum of the plaintext checksums the random data, so you learn nothing from it. And this is only partial because it doesn't work for images or non-XML files. Then there was this issue in the Oasis bug tracker from Dennis Hamilton 10 years ago. It contained two ideas. One was to replace the plaintext checksum with HMAC SHA-1 get towards authentication. Yeah, nowadays we wouldn't use SHA-1 anymore. And then the second idea was to add another salt for the start key derivation step. So that's the one before the key derivation function. And I didn't understand what problem this would solve. And yeah, elsewhere in Microsoft Office, OXML itself does not have any standardized encryption, but there is an implementation in Microsoft Office where they store an entire OXML document in a wrapper OLE2 storage. The entire OXML is encrypted there. Yeah, okay, so then what did we come up with as a solution to the problems? So first, for the performance problem, obviously it's just a dumb idea to encrypt every entry in the zip file separately. What we should do instead is we produce an unencrypted ODF package that's just like a normal one. Then we encrypt the whole thing with a single key. So we run the KDF only once. And then we store the result as a single entry with a magic name encrypted package in a wrapper ODF package. And this wrapper package contains only this and the manifest XML, and maybe if the document is signed, it can contain the digital signatures. So for the second problem, authentication, there are two options basically how we could get that HMAC function. That essentially means we create a second key somehow, and then we hash the key and the ciphertext with hash function and store that in the manifest. Then we would know the document has been tampered with, and the other option is what's called an AEAD function, that is automated encryption with additional data. So essentially that means that the encryption algorithm produces, in addition to the encrypted data, also a tag which is then stored in the file. And if the decryption key doesn't match, then checking the tag will fail on the decryption. There is this ASGCM algorithm that is very popular. It's already in TLS standard and so on. And both of these options are widely available in libraries which we already use in LibreOffice, such as NFSL. Yeah, we didn't really see any compelling argument to choose one over the other, so we just went with GCM in the end. Then third problem, I'd like to have a key derivation function that is memory hard. So our customer pointed us to Argon 2 ID. That is a function that can use a configurable amount of memory, and that will then prevent the very parallel GPU brute forcing. So GPU doesn't have enough memory. This is also standardized by the IETF as RFC 106. And those of you who are using Linux might already be familiar with it. It's used in Lux2 storage encryption. On my laptop, it's using 1 gigabyte of memory. And yeah, I have a fun anecdote to tell about this, but that would take 10 minutes. This IFC contains a list of various parameters that are recommended, and we choose one of these sets of parameters that is using 64 megabytes of memory. Using that would be a bit difficult with, we still have 32-bit Windows builds. Wouldn't work well there. At the time when we started this, there wasn't an implementation in NSS or OpenSSL of Argon, but there is a reference library which has a license that's suitable for LibreOffice. No problems there. Okay, so summary of the solutions. So solve the performance problem by storing a single encrypted ODF package in a wrapper. For authentication, it's an AED function. And then to get a memory hard KDF, we ASP KDF2 with Argon 2 ID. And as for the information leaks, if we use authenticated encryption, then having a plain text checksum is just pointless. We can just leave it out. And the entries, the names of the zip entries will be in the inner package, which is encrypted, so no longer visible. That problem is also solved. So then we went about implementing this. The SVX2 code in medium SVX object was a bit more complex than expected, particularly when it gets to adding the digital signatures. So it closes the file and then opens it in a whole different storage mode for that, and there are lots of different storage and stream variables using usage. And the other big module that had to change was the package module. It was also a bit complex. That was my least favorite feature. You can store basic macros in your ODF file, and then you can also password protect these basic libraries, and it's just it stores the macro itself, the source code, encrypted, but then it also stores an unencrypted bytecode representation of the same macro, so what's the point? And in order to implement this feature, the package module has the ability to serialize all of the parameters that are used for encryption into a stream and write that into a temp file and then read it out again and deserialize it, and just so it can transfer an encrypted macro from one document to another document. To get Argon 2 to work, we just had to bundle the reference implementation, which was not terribly difficult except for Windows on ARM, which thankfully somebody other than me solved. I think it was So what is the status now of this? The new ODF encryption is shipping with the 24.2 release, but only if you enable the experimental features. Because, as I already mentioned, if you store such a file, you can not open it with an LibreOffice version older than 24.2. It's just necessarily incompatible. And in the current release 24.8, it is enabled by default if you leave the ODF version in Tools Options at its default of 1.3 extended, switch to non-extended, you get the previous slow implementation. There is also just a quick note, an environment variable where you can disable Argon 2 and go back to EKDF2, but otherwise use the new doing things and with an additional increase in the number of iterations, so 600,000. I don't think this is practical use, it's just for testing basically. And yeah, then for ODF, we have submitted a proposal for this. It was already discussed in the TC, and Microsoft brought on one of their cryptographic experts, and their proposal was accepted. And it will be in ODF 1.5 eventually. Yes. Yeah, and of course, our customer, ESI, for funding this work would not have been possible without this, and they also there was one of their cryptographic experts to talk to and review. Yes. So, yeah, thank you for that.